Yesterday we spent some time taking a look at charges moving through wires in external magnetic fields. Current-carrying conductors, we call them sometimes. There's a wire, carries an electron current going through it to the right through a magnetic field that points downwards towards the bottom of the page. We can figure out the direction of the force on that wire by using the hand rule, the hand rule for deflection. It goes thumb in the direction of the current, fingers in the direction of the field, palm points out of the page. So there would be a force on this wire acting out of the page. Agree with that? We can find the magnitude of that force using the equation F is equal to ILB. Agree with that? All right, we're set for today's activity then. Today's activity is called the Current Balance Lab. In the Current Balance Lab, we're essentially going to show that what we've learned about wires in external magnetic fields over the last day or so is correct. It's going to involve two parts. Part A, or part 1, is going to involve an apparatus that looks like this. You're going to see a power supply. You're going to see a scale that measures to the nearest hundredth of a gram. Sitting on that scale is a little magnet. I don't know if you can really make that out in the picture or not, but really what it amounts to is, if we look at a cross-section of that magnet, it looks like this, with a north pole and a south pole. In the little gap there is a little printed circuit. That printed circuit has a wire. So if we apply a current through that wire, then all of a sudden we've got a current that's in between that north pole and south pole. In other words, we've got a current through a wire in an external magnetic field. So the idea here is this. We fire up this power supply. We allow an electric current to flow through the wire to one arm, one conducting arm of this apparatus here, through that little wire, around the other side, and then back to the power supply. That allows an electric current, again, to flow through that wire that's exposed to the external magnetic field. That wire will experience a force. Now, we could figure out what the direction of that force is, but that's not the purpose of today's activity. Okay, we know that it's going to experience a force. The direction of that force isn't really a huge deal, one way or the other. What we're more concerned about today is the magnitude of that force. Well, how do we find the magnitude of the force on that wire as it carries a current through that magnetic field? Well, we're going to find it kind of indirectly. You know that if object A applies a force on object B, then object B will apply an equal and opposite force on object A. So if the magnets apply a force on the wire, then the wire will apply a force on the magnets. The magnets are sitting on top of a scale here. If we have this scale turned on and these magnets are pushed down by the wire, then the scale is going to be tricked into thinking the magnets are heavier than they really are. We're going to record the value of the mass that the scale reads, and then we're going to convert that to a force. That will be our magnetic force. Does that make a little bit of sense? In the first experiment, you're going to keep the length of wire constant. We can change this little insert right here. This little insert right here, this printed circuit that has the wire in it, we can change that to make it up to 6 different lengths. But in the first experiment, you're going to keep it the same length. Doesn't matter what it is, preferably one of the longer lengths, but it's not really a huge deal if you forget that and make it one of the shorter ones. Bottom line is, you got to keep it the same. You want to put it literally in between these two poles of this magnet here. Okay, we got a north pole, we got a south pole, put it in between. Make sure it's not touching either of the poles. Make sure it's not touching the magnets anywhere. Okay, but make sure that it is in between. Okay, not above it, not touching it, not knocking it down, whatever. Then on the power supply, we're going to adjust the current. You see here that we've got the current knob, which is on the bottom, turned as far to the right as you can go, as far as it'll go on the right. And then you're going to turn the voltage knob up a little bit at a time, changing the value of the current. Because the value of the current is going to change, you're going to find that the reading on the scale is also going to change. We're going to record the current, which we're going to read off of the power supply, and the mass on the scale, the mass reading on the scale, right here and right here. Change the value of the current, get another one, get another mass. Change the value of the current, get another mass. By the way, why do I have mass in quotation marks there? It's not really the mass that we're measuring, right? The scale is tricked into thinking that it's mass. The scale thinks that there's more mass on there because the magnets are being pushed down, but it's not really more mass. It just thinks it is. Once we have 10 trials of current and mass, and by the way, the wire length you should record, but it's going to be the same for all of my trials. Once you have 10 of those trials, then what we're going to do is find a magnetic force. I'll show you how to do that in just a second after I show you how to do the second experiment. The second experiment involves almost the same thing, certainly the same apparatus, but instead of keeping the length of wire constant, you're going to keep the current constant this time. I would set it somewhere around 1 amp. It doesn't have to be exact. Okay, if you're having a little bit of trouble adjusting it to exactly 1 amp, that's fine. 0.95, 1.02, 1.1, 1.5 would even be fine. It doesn't really matter. 1 amp just seems to be a good round number if you can get it somewhere around there. Now instead of manipulating the current, you're going to manipulate the length of wire. These are the little inserts that we take out of the package and then plug into the apparatus. In between changing these inserts, in between changing these lengths of wire, I want you to turn the power supply off. So in other words, as you touch bare wire, make sure there's no current flowing through that wire. Does that make sense? You're going to do that 6 times. The reason you're only going to do that 6 times as opposed to 10 times is because we only have 6 different inserts, 6 different lengths of wire. Okay, 1 current now that's kept the same. 6 different lengths of wire, 6 different masses. Not really mass, right? But what the scale thinks is mass. Once we have our 2 data tables, we've got to find the magnetic force. The magnetic force, in both cases, whether it's experiment 1 or experiment 2, is going to be found in the same way. We're going to take the mass in grams. We're going to convert it to kilograms by dividing by 1,000. And then the kilograms, we're going to multiply by 9.81. That's going to give us the magnetic force. So the magnetic force acting on this magnet that's pushing down on this scale is equal to the kilograms, the mass in kilograms, multiplied by 9.81. Same thing over here, right? Same thing right here. What do you think you're going to do now? You got 2 different analysis tables. What are you normally going to do with an analysis table? You're going to graph it. You're going to plot 2 graphs. The first graph is going to be magnetic force versus current. The second graph is going to be magnetic force versus wire length. The first graph should look something like this. When you plot it, the points will be almost certainly a perfect straight line, at least almost a perfect straight line. The data for this activity usually works out really, really good. We expect to get a straight line, we will get a straight line, and it's going to be almost perfect. You're going to have no trouble seeing that it's supposed to be a straight line whatsoever. Draw your line of best fit. If you're not plotting on an Excel, then draw your line of best fit, find the value of the slope. If you are doing it on Excel, then have Excel draw your line of best fit and have Excel calculate the slope for you. Then I want you to go through a similar analysis to what we did on our momentum lab, although this one's a little bit easier. The equation for any straight line graph is what? Whether it's this one or the momentum lab or V equals V versus T. Y is equal to mx plus b. This is the equation that describes this graph or any other straight line graph. Now, specifically this graph, my y-axis is magnetic force. M is my slope. My x-axis is my current. And there should be no y-intercept. So we can scratch that one out. But we also need an equation from our data sheet that matches up with that has the same variables in there. Which equation on your data sheet has both magnetic force and current on it? I'll give you a hint. We just did it. ILB. Good. The force appears in both, so get rid of it. The current appears in both, so get rid of it. What we're left with here now is the slope in the equation that comes from the graph, and the length times the magnetic field in the equation that comes from the data sheet. Therefore, we're going to say the slope of this graph is equal to the length of the wire times the magnetic field strength. Now, the slope of the graph you're going to get from your Excel calculation or from your calculation that you do by hand. The length of the wire was kept constant in this experiment, so you've got its value recorded. What I want you to do there is calculate the value of the magnetic field. Now, 5 minutes ago, if you had a saw force versus current graph, you would have had no idea how to find the magnetic field from a force versus current graph. Now you do. But more important than finding the magnetic field from a force versus current graph per se is this analysis, how we got the magnetic field from that. Not what the magnetic field is, but how we got it. There's two purposes to the activity that we're doing today. Okay, the first purpose is to put into practice what we've been doing over the last couple of days with magnetic force on wires. The second purpose is to go through this analysis with graphs that we've never seen before. You will get one question on your diploma exam. One, a single question that's worth 2% of your diploma exam, 1% of your overall physics 30 grade, that is a graphing question. There's a good chance it'll be a graph that you've never seen before. If you get lucky, it may be a graph that we have seen before. You will need to analyze that graph and find out something. Like, for instance, on this graph, finding the value of the magnetic field. You will go through this process. You will say y equals mx plus b. You will get an equation from your data sheet. You'll cross off things that appear in both. You'll figure out what the slope means, and from that, you'll get what you need to get. Okay? Does that analysis make sense? I hope it does. But if it doesn't, good news is we have another one. Force versus wire length. This is our second experiment, right? It's also going to be a straight line graph. We need an equation from the graph and an equation from our data sheet. What's the equation that describes this graph? It's a straight line graph, right? So what is it? Y equals mx plus b. Looks so far so good. You guys are superstars on this so far. What's on the y-axis? Force. M means slope. What's on my x-axis? The wire length. And the y-intercept, there's not going to be one. What's the equation on my data sheet that has both F and L in it? Same one as we had in the last one, right? F is equal to ILB. Let's cross off things that appear in both. Force disappears. L disappears. What's the slope equal to in this case? I times B. We can get the value of the slope. We have the value of the current. It was the 1 amp, right? Or whatever it is that you're whatever the value of the current is that you're keeping the same. We can rearrange it to solve for the magnetic field. What should you notice about the magnetic field that we find in experiment 1 versus the magnetic field that we find in experiment 2? They should be the same. Why? Because you're calculating the same? It's more basic than that. Here's the magnet. Did we change it? The magnet was the same. The current stayed the same throughout trial 2. The wire length stayed the same throughout trial 1. But the magnet stayed the same throughout the entire thing. Right? So the magnetic field that we find in experiment 1 should be the same as the magnetic field that we find in experiment 2. More or less, at least. Now, what do you got to hand in for this? Here's the good news. Because the purpose of this lab was just to illustrate some of the stuff that we've been doing over the last couple days and to do this graphing stuff right here that you see up on the board. I'm not going to ask you to do a full lab write-up for this. It is literally just the data that you collect today and the analysis, which includes the calculation of magnetic force for both experiments, which includes the graph for both experiments, and the determination of the magnetic field in both experiments. Got it? All right, we're going to break up into groups of, let's say, 3-ish, give or take one. And we're going to have one group go on this experiment at a time. We only have one apparatus because of the cost of the scale. So we're going to have one group go at a time. The other groups are going to be working on multiple choice questions as practice in preparation for next Thursday's test. If you finish those multiple choice questions, then you're going to work on something productive in physics and ask me questions in preparation for next Thursday's test. Okay? This experiment, by the way, will be due on Tuesday, but it's a quick 15-minute write-up, literally 15, 20-minute write-up. So you can even get it done tonight and have no homework over the long weekend. All right, let's get at it, guys.